This is Rosen 13.3 on finite state automata. Here we discuss what is called the non-deterministic finite state automaton. And an NFSA, as we'll call it, and for non-deterministic, is also like what we'll call a deterministic finite state automaton, a 5-tuple, where we have a set S of states, input alphabet, a transition function. Now this is the new thing. Instead of assigning a state and input pair to another state, it assigns a state and input pair to a set of states, so that really our function is from S cross I to the power set of S. And again, we'll have the initial state and the set of final or accepting states. Okay, well, let's take a look at how this works. For an NFSA, we can use a state table where we give a list of possible next states for each pair of state and input value. So it could be more than one. In fact, we expect it to be more than one. It could be none. Then we construct a state diagram by including an edge from each state to all possible next states. And because of that, I like to think of these as branching automata, because we actually explore every possible next state when we do this. And again, we use NFSA for non-deterministic FSA, DFSA for deterministic FSA. That's what we've been studying, where we have one and only one next state for every state and input pair. All right, so let's take a look at what these look like. First, we'll look at a table. And here's our state transition function. And remember, we map from a state and input to a set of states. So for S0 and 1, we go to state 3, but for S0 and 0, we go to 2 different states. And note for S2 and 0, there's no states that we go to. And for S3 and 0, we go to 3 possible states. Whereas if 1 comes in, we only go to 1 other state. So how will we draw that? Well, we have to have the final states designated. They're S2 and S3. And we start in state S0. So here's how it works. We have a non-accepting S0, non-accepting S1, accepting S2, and accepting S3. S0, S1, S2, and S3. We're starting in state 0. And so in state 0, if a 0 comes in, I'm going to go to state 0 here, but I'm also going to go to state 1 here. And if I'm in state 2 and a 0 comes in, nothing happens. And if, in fact, I map to the empty set, there's the machine errors. If a 1 comes in, I stay in state 2 and I go to state 0. If I'm in state 3, and a 0 comes in, I'm going to go to 3 different states, state 2, state 0, and state 1. Whereas if a 1 comes in, I'm only going to go to state 1. Okay? And we'll see that this branching ability for non-deterministic finite state automata has some power to it in terms of creating efficient machines. Let's look at how an NFSA can recognize language. Here we have an NFSA where state 0 can map to 2 different states, and I have 2 mappings to no states at all. Well, what does this machine recognize? Well, we can see from before that this machine is going to recognize 0 to the n for n non-negative. And then it's going to, as the zeros come in, it's going to continue to branch and go down to the state 2, but then state 2 does nothing with additional zeros. But if a 1 comes in after some number of zeros, then it does transition to S4. So that means 0 to the n, and then a following a 0 and a 1 is recognized. And then if we could take this path here, if a 1 ever comes in, we go to state 1. And then if another 1 comes in, we go to state S4. So that would give us 0 to the n, 1. 1 would be recognized. And then if anything came in after any of those recognition, the second two recognition uh, uh, patterns, then we go to a state of perpetual non-recognition. So those three patterns uh, would define the language that is recognized by this non-deterministic finite state automaton.